Okay, so I'm going to review a lot of things that you've already been through. I'd like to just make one more video of chapters 3 and 4 as kind of an overview review because we've actually covered a lot of cognition in the materials that you have in your chapter 3-4 folder. And we're pretty soon to move on to attention. And from here on in, if you don't have really the basics of this unit, then you're going to have some trouble. So, first of all, if I were to look across chapters 3 and 4 together, I'd say that they are about how early low-level visual perception and high-level visual perception happen together in parallel. And then we introduce the terms top-down and bottom-up processing, and then you remember that bottom up, of course, means sort of stimulus driven, feature based, very low level, very early. We talk about features being processed in parallel, very automatically. On the other hand, we talk about top down processing as involving prior knowledge or experience. Sometimes top down processing requires no real awareness at all. Yet it still reflects understanding based on past experience, and we'll look at some examples of that. And again, I'm just going to say again that I'm going to go through some things somewhat quickly on these slides because I've already talked about them, but I really would like to give you an overview review. So let's move on. This is just an interesting picture from the book. All I want you to know for our purposes, just as explained in the book, this central square is the same darkness as this square. There are both low-level processes that support that illusion and high-level processes. I am not going to ask you to explain lateral inhibition. It's a little too sensation-ish. In other words, if you take a course in sensation, you might go through it in detail. It's also a bit advanced for a first semester in cognition. But all I want you to understand is that lateral inhibition enhances contrast, especially contour, and that's very good for helping us perceive objects. So it's a low-level phenomenon that helps us perceive objects. At the same time, there are top-down influences on why you perceive this square as dark and this one as slightly lighter. First of all, you see this is in a shadow. It's in a shadow of this cylinder, but it's also a white square. You perceive it to be a white square. So your mind wants to see it as a little bit darker, but not by any means as dark as the dark square. So it's a nice example of top-down and bottom-up perception happening at the same time. What's the point of these cubes? I think this is somewhat clear in the book, but the obvious point is that you can see these two ambiguous cubes in either of two ways, but you will never see them as the average of those two ways. You see them as one way or another. And in fact, once you kind of practice, you can toggle back and forth. But again, you'll never see the average of the two possibilities. Why is that? Well, what I'd like you to think about is that, remember our course theme, cognition is about working efficiently, quickly, accurately as possible while not being perfect, but again, working as efficiently as possible. And in fact, out in the world, the average of two possibilities makes no sense. So you can see an object one way or you can see it another, but it makes no sense to sort of pick the in-between version. So it's ambiguous and your perception system chooses one way or another. Just some more examples that I think are pretty clear from the book. The purpose of this slide is just to remind us that part of the Really one of the biggest tasks of the perception system is to identify objects. The visual scene consists of objects that are acting in the world, objects and actions. What is it? Where is it? And of course, where might uh, be especially important if it's moving. Where is it in relation to me? Um, but we don't often get a perfect look at an object. So the point of these four cats is each one is in a completely different position. We're seeing it from a different orientation. And in some cases, where a lot of the kitten is obscured. So your perception system needs to get to the object identification despite a very messy, incomplete visual scene. Here, just another example from the book. The character, the H or the A, in the center of each word is obviously the same. A fluent reader would have no trouble taking this ambiguous stimulus and making the right inference in each case. And of course, that must be top-down processing, because remember that the bottom-up perception gives us the same information in both the and the word cat. So the ambiguous stimulus in the center of each word is the exact same. So we need top-down support from context to get to the correct object. Here I just put up a kind of a CAPTCHA. You probably know this when you log on to a bank, a you're at a website, you want to log into a bank to take out to transfer some money or whatever you might want to do. You often have to enter messy characters called a CAPTCHA. Well, why is that? Well, identifying messy characters is a very top-down process. A computer would have a hard time emulating a human mind. Think about this for a second. Artificial intelligence scientists have been working for 50, 60 years to imitate basic human perception. My 5-year-old child does not walk off cliffs, walk into trees. She doesn't have trouble figuring out what is a hole in the sand versus a bump in the sand, right? These are obvious, easy feats of human perception, but imitating them for a computer is quite difficult. And think about the fact that artificial intelligence begins sometime in our 60s and 70s and 80s and 90s, and we are just now in 2016 beginning to appreciate that maybe there'll be driverless cars. So all of the examples that I go through involving top-down perception, I want you to sort of appreciate that there are things that a 5-year-old child could do really easily, for the most part. And then they're actually very difficult to imitate with computers. By the way, I said 5-year-old childs for the most part, because it turns out that some top-down perceptions are somewhat slow developing. For example, judging the distance of objects, which is very top-down, is difficult for younger children. This is just called the Ames room illusion. The Ames room illusion is created by, well, it's a trick. It's a trick room. There's two girls that are obviously the same person. One is in the foreground, one is in the background. One's made to look like a giant, one's made to look like a mini person. Of course, you can see that what's really happened as the creators of this room have created an odd-shaped room. It's certainly not a square or a rectangle. And they've cheated with lines and shadows so that the image appears to convey depth information in a way that's very deceiving. You can tell the depth information cues are all wrong. So here they're just messing with your top-down perception. You've already seen, and I promise you're going to learn new things on this set of slides, and it's really going to be worth your time, I think, and yet I know that I'm giving you some review. In my face-to-face classes, sometimes I like to take a step back and step back through everything after you've been through it once, and then you can really, I hope, kind of integrate and make sure that you really understand things. I'd like you to think about Gestalt perception as all top-down processing. Maybe the interesting thing about Gestalt perception is that we have developed these sort of mental shortcuts or heuristics that we follow to help us identify objects. And these several principles identified by the Gestalt people, we all seem to use. So these are top-down, they're experience-based, and yet they're common to all of us. So in a way, it's a lot like the book's discussion of pictorial cues for depth. We need experience to develop them, but we all develop the same ones. We all live in the same kind of environment. This is my messy room slide. Just you can look at all the examples of a Gestalt. You could find a Gestalt example for just about every thing we've gone through. You can see that your top-down perception tells you that this Dr. Pepper can has to be fake. It's a balloon or a pillow or something like that. It's surely not a Dr. Pepper can. The relative size is wrong. A couple pictures. Just cognitive scientists who like to make trick pictures. You can tell this cat climbing around a pole cannot be one cat, but the artist has played with the feeling of continuation, lines that look, so you can just sort of imagine continuous lines here. They've lined it up perfectly, and that creates the feeling of a single object. But of course, no cat could be stretched out like that. I love this illusory contour slide, this example. You have the strong feeling of one triangle floating on top of another. And yet you know this can't be true. There's no triangle. In fact, if you're like me, you really, really, really feel like you're seeing lines, three legs of a triangle, but you know you're not. Those are called illusory contours. That is a really nice example of construction because you're taking the visual stimulus and you're adding something. In this case, you're adding contours, lines to make up a triangle, and they're not there. Size distance. The book has several examples of pictorial cues to depth. You should be able to use the book and apply them right here. Remember, pictures don't have depth. They're two-dimensional. So literally, that picture of hot air balloons is two-dimensional. There is no depth. However, you certainly feel like the little balloon is furthest away, but you must be using pictorial cues to depth to make that judgment. Again, that's obvious because you're looking at a flat picture. And in this case, you have the sense that all hot air balloons are about the same size, and so the smallest one must be the furthest away. This is a nice example of parallel lines converging as they move toward the horizon. Here we see the texture of the foreground, a little bit blurrier in the middle ground, and really washed out in the faraway ground. Artists develop experience at creating illusions of depth, illusions of perspective. The moon illusion. I won't say a lot about it, not now, but I'll just tell you what it is because it's next time you see it, I hope, like me, think it's really a beautiful illusion. You're driving down the highway, you see a full moon low on the horizon, and the key is low on the horizon. And what you do is you perceive it to be much, much bigger than on other times when you see a full moon that's higher up in the air. all I'll say for now is I think this is a very interesting top-down perception illusion for some where we amplify the moon because we feel like it must be really big because it's very far away, and yet its apparent size is that of, say, this tree. We went through, you went through a whole unit on visual search. Let me just say a few things here. First of all, this is clearly a feature search. You're looking for a vertical line in a field of horizontal distractors. So as we increase in distractors trial by trial, your reaction time will not increase. So independent measure, number of distractors, dependent measure, target. As we increase distractors, search time will not increase. Why is that? Very simply, you get early, low-level, parallel processing of features because you have feature neurons early in visual cortex, occipital lobe, no doubt. And in this case, there is no overlap between target and distractors. So you would expect to see rich top-down support. I'm sorry, I scratched that. So let me just undo that statement without rewinding. We would get no top-down support. This is a bottom-up, feature-based search. Color. Green pops out in a field of red. So again, this is a bottom-up parallel search. I just used the word pop-out there. Remember that pop-out is the term we use for this fast, effortless search. You don't have the experience, you don't have the sort of subjective of experience of looking for the green line. It just jumps out at you. That's pop-out. On the other hand, in this case, you're looking for a red vertical line in a field of red horizontal lines and green vertical lines. So in this search, you do not get pop-out. Instead, you have the sort of subjective experience of having to step through each distractor and rule it out. No, 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 no. Oh, there it is. So as distractors increase, we expect RT to increase quite a bit. So if you were to graph this, you'd graph an upward rising diagonal line showing that the more distractors, the slower you are. In this case, so again, why is this a slow search? I'm going to call this a top-down search. You have to use top-down processes to find it. Why is this a slow search? Because the target has two features, verticalness and redness, and those same two features overlap with the distractors. The distractors are verticals, in this case greens, and reds. So vertical and red is part of the distractor, and it's also part of the target. So let's see. This must be the word work. Why is that? Well, because you read, you can make this W, O, R, and this, it could be an R or it could be a K. But if it's an R, W, O, R, R, it's just not a word. So this is just another example I want to give you of top-down perception. Let's see. This is what do you call it? An anagram when you need to unscramble the word and identify it. Here's another anagram. And I actually not totally sure if I loaded the paragraph of that I will tell you what, I will load it after this. It's a paragraph of all scrambled words. And what I'd like you to get, just open it up and read it. And it's actually a paragraph of scrambled words that I predict you will be able to read at approximately a normal pace. It's just a really nice example of top-down perception. Interestingly, in the paragraph, as you read it, it says that you can read this so well because you only read the first and the last letter of each word. I think that is completely wrong. So once again, it's a very interesting paragraph because you can read it automatically, but the paragraph provides an explanation that's wrong. Let me explain why I can say that so confidently. First of all, is this top down or bottom up? The fact that you can read a scrambled paragraph. Well, it must be top down. So what kinds of experience make you able to do this? Well, the paragraph provides context. It's about something. As you read along, you get a sense of what it's about. There are no random sentences or random words within a sentence. They all make sense based on context. Also, you're getting what I would call implicit, in other words, automatic, unconscious, support from grammar knowledge. What do I mean by grammar knowledge? Well, let's say I have a sentence in which I use the word the. What kind of a word are you looking for after a the? Are you looking for a verb, as in the running was green? Of course not. The running was green makes no sense. You're looking for a noun, as in the apple was green. So you get implicit support by grammar. You probably get a little bit of implicit support by sound letter knowledge. So in other words, if a word let's say this bottom word begins with R, what kind of a letter comes after R? Well, I'd say probably a vowel. There are not a lot of consonants that would work there. In fact, I can think of a few words that go RH, starting with R and then go H, but not many. Rhododendron, I think. But really, how many consonants work there? So again, implicit support or I'm getting an implicit boost from my understanding of what letters go together commonly in English. Again, I know that I'm reviewing things, but what I'm trying to do here, I want you to keep this in mind when we start talking about recency and frequency and priming, because it should all start coming together. So in this paragraph, which I will definitely load for you just in case it wasn't in one of my earlier videos, appreciate that you get support from many levels, and interestingly, the paragraph's own explanation is really poor. Word superiority effect. I also will load my little PowerPoint, which I know I didn't load. Truthfully, I just, it's not, I'm going to load a little PowerPoint thing so you can sort of do the word superiority effect yourself. I'd say it's a fairly poor imitation of the real word superiority effect because it's in PowerPoint. In the real word superiority effect, words were presented very fast, something like 30 milliseconds, faster than you can blink. So fast that you really would not be aware that you're clearly reading the word. In my demo, it's a few times slower than that. And when the word appears, you'll have no trouble reading it. When the letter string appears, you will not be able to read the letter string. Probably, maybe you will be able to. But so what's the definition of the word superiority effect? Letters are identified more quickly within a real word than a non-word. But I also want you to pay very careful attention to the text when they give a few other examples, because letters are easier to identify within a pseudo word as opposed to a non-pseudo word. When I say pseudo word, I mean a non-word that has a plausible spelling. B-L-A-T is not a word. Actually, it might be a word, but let's just say it's not a word. B-L-A-T, not a word. But it's a legal English spelling. B-L-X-T is not. So indeed, T would be easier to identify in blat as opposed to blixt. And that's really important to appreciate because it reminds us that in addition to getting support from the word level, sort of top-down support from word knowledge, we're also getting top-down support from experience with English sound letter combinations. I like the sort of more English-like a word is, the more likely you are able to get it. So this is just the definition as it is in the book. So this is a nice graph showing you you get a higher percentage when the letter appears within a word as opposed to by itself. And here again, this is clearly straight from the book, but I want you to pay attention to this. Phonology. Let me define phonology. Phonology is the sounds that make up your language. So cat has 3 sounds, k, a, t. Those are actually called phonemes, and sort of all of the sounds are the phonology of language. It's not important. Well, actually, I should remember that I've already used the word phonological loop. It's interesting to think about pronounceability. We get support from pronounceability. And remember that's interesting to think about when you remember that you have a phonological loop in working memory that's very good at holding sound information online. And that makes sense because in typical development, we process sound to understand language. Errors. I think the book makes this really clear. But in errors, we typically regularize, meaning we are more likely to make an error that makes sense. This is, again, just really nice example of top-down processing. If you make an error based in a probabilistic way, meaning you read it wrong, but you read it wrong in a way that would be right many times, right by context, then you're showing top-down perception. Okay, now we're getting into important stuff. I want you to pay some attention to this graph in the text and think about frequency and think about recency. Think about the word that you probably have heard as much as any other word. Let's eliminate words like the and a, sort of grammar words. Just for this example, what word have you heard many, many, many times? And I hope you've heard it in the last week. Your name. So your name has been heard frequently and it's been heard recently. To use the book's analogy, you have detectors. Now, I think I will try to load a picture that I don't have in this slide. A kind of a crude picture that I could just sort of draw as if I were drawing on the board. But for right now, I'm going to explain it. So we've talked about how we have early processing and later processing. Let's think about vision right now. At the earliest stage in the visual system, we have feature neurons that are coding for simple features. However, when we perceive an object, we have to get from simple features to a complex object. So think of a house. To identify a house, you have to be sensitive to the parts, not just the basic features, but the parts. And so imagine that feature neurons fire on other neurons in a hierarchical way, such that we have feature detectors that just fire to lines, and then we have feature detectors that might receive input from line detectors that might code for something like a corner, which really is two lines together, or a certain shape. And so, in a sort of theoretical way, you could think of a feature detector coding for something very basic, and then in sort of a pyramid-like way, getting downstream to a feature detector to something more high level, like your name. So I don't mean that your name is a feature. It is not. Your name is a concept. It's an English word. But I want you to appreciate that. In this case, that would be an auditory example. We have auditory features. You have Think about how the fact that you have detectors that sort of detect different stimuli, including some higher level stimuli. So when those detectors get when they, let's say my name is Eric. The word Eric for me, to use the book's sort of analogy, the word Eric is warmed up. In other words, the Eric detector has fired a lot. It's fired recently and it fires frequently. Therefore, the word Eric for me, probably not for you, is continuously warmed up. It requires less input to fire. So if you look at if you read the book's description of presenting masked words, they're presented very quickly. It's hard to identify words presented very quickly. However, words that are frequent are going to require less input to fire. That's a recency effect or a frequency effect. So go through this, with this in mind, go through this carefully and really spend some time thinking about the fact that detectors are hierarchical in the sense that we have very, very basic feature detectors at the lowest level. And at higher levels, we have things coming together into meaningful percepts, things that you perceive. And then keep in your mind that both repetition, and frequency prime. Frequency really is frequency just means you've heard it, you hear it a lot. Repetition, if something gets repeated, it means you've heard it recently. Then we went through the recognition by components theory. I wanted you to I know you've gone through this in some detail, but I'm just going to kind of give you a quick overview. First of all, you have to appreciate that a geon is sort of analogous to a feature, but it's not a feature. Features are two-dimensional, like a line. Geons are three-dimensional, and so they're sort of feature-like. What I mean by feature-like is that objects can be broken down into basic geons. The other thing that you have to get to understand recognition by components theory is that this is a bottom-up theory. That might be confusing because you certainly need experience in the world to get basic geons. In other words, if you didn't have any time in the world, you wouldn't have enough visual experience to sort of develop a set of basic volumes that could make up any object. So I know that's a little bit confusing, but just accept that you need a little bit of experience to develop a set of geons in your memory. However, I want you to keep in mind that it's a bottom-up theory. You perceive an object, and in a bottom-up way, you immediately, using parallel processing, break the object up into a set of geons. Why do we like this theory? What good does it do us? Well, remember that the sort of million-dollar question in perception is really about how do we recognize objects so quickly, so efficiently, so easily, despite what a difficult task it is. And if you've read my essay on perception or gone through the rest of the materials, then you really know what I mean when I say a difficult task. I hope you know that. Well, a few pluses in terms of the Guion theory. One, it uses bottom-up parallel processing to rapidly get Guions. You don't need to see all of the Guions of an object to recognize it. Really, you just need a couple, 2, 3. It's Guions are viewpoint invariant or view independent. All that really means is that you can recognize them easily from just about any angle. And they're resistant to visual noise. All that means is in a messy visual world, which is like the world we live in, you can still typically see the Guions. You don't need to see the object clearly to get the basic Guions. Just a nice picture from the book illustrating this. This demo, which I'm just stepping through because it's in your book, you can do it yourself. But look here, let's take this glass. With these lines appear somewhat continuous. You can kind of use your Gestalt perception to fill in a curve. If you do that, you're getting a basic sense of the Guion. So you have enough to make a guess of what it is. Let me go back a bit. In this case, you don't have enough information. Look at this. This could be a flower or I don't know what else. The reason it doesn't jump out at you like it does now is because in the first picture, you didn't have enough information to get the Guion. Once you get the Guion, it's pretty easy to get to the object. Okay. Now, what do we mean by view dependent versus view independent? This is quite important. So back to view dependence and view independence. Well, first of all, a central point about the Guion theory is that objects can be viewed about equally well from any perspective. Now, that's true and sort of obviously true for many objects. So imagine I held up a book and I kind of rotated it in the air and I just showed it to you from different angles. And imagine I had you identify it from different angles. In this simple thought experiment, you can probably appreciate that you do about as well identifying the book from any view. However, an alternative point of view, an alternative perceptual theory for object identification posits that we perceive objects in a viewpoint dependent way. And you should read this carefully in the book because it's not that obvious. But the idea goes like this. You have a stored set of sort of model viewpoints for each object. So when I say a model viewpoint, I mean, imagine for every object, you have 4 or 5 stored views, front, back, side, angle, that sort of thing. And out in the world, you will all the time see the object from a novel view, from a new view that you've never seen before. And you're going to have the difficult job of deciding what that object is. According to the viewpoint dependent perspective, you actually perform a mental rotation. And indeed, there's some evidence that for object identification, the further you would need to rotate it, the more in your mind, the slower reaction time for identification would be. I'd like you to understand that the Guion perspective is view independent. That's really important. And I'd like you to know the view dependent perspective, just as I've said it. And then critically, when we get to faces, you should understand that faces are the best example I can give you of viewpoint dependent objects. This is just some review of bottom up, top down. Remember that in any scene, we do some feature perception. That's bottom up. Guion's bottom up. And these blurry pictures, which don't show up that well, actually all the artist has done is made a blob and kind of put it in the same three pictures. And interestingly, you make a top-down judgment as to what the blob is simply based on context. Just an example of top-down perception. Now this slide is a slide from the book that is well worth a minute to look at it. First of all, you're looking at it from upside down. Brains, when looked at from upside down, it kind of makes me think of a turkey. This is the front. This is the back. These are the temporal lobes. So let's look at this 130 millisecond slide. We see some activation in the occipital cortex. This is sort of occipital temporal. I shouldn't have said occipital. I should say occipital into temporal. And then up here, this is the frontal lobe. We see some activation in the frontal lobe. So this is a very interesting slide, and let me talk about what it's demonstrating. The take-home message, that's what I want you to get here. The take-home message, this was an object identification task, and we saw activation in the frontal cortex ahead of the occipital cortex, or the occipital temporal cortex. So if I show you an object, if I'm giving you a visual perception task, it is a certainty that you will perceive, you will get activation in your occipital cortex into your temporal cortex. Because remember, visual perception begins in the occipital lobe, and the temporal lobe is where our what pathway is. So it's an absolute certainty that you're going to get early activation in the occipital lobe spreading into the temporal lobe. So why would you get activation in this condition earlier in the frontal lobe? And of course, it's because these participants were anticipating something. They expected something. They were showing an expectancy effect. So they were showing some priming based on what they expected. And if you have an expectancy, then you're showing a nice top-down perception, a very high-level process that involves the frontal lobe. So that's a nice frontal illustration of frontal activation showing expectancy. Yeah, semantic priming. I want you to know the word semantic. Semantic in cognition means based on meaning. So semantic priming is priming based on meaning. So later in the semester, we'll see a priming example where participants hear the word bank. And there are two different meanings of the word bank. You can sit on the bank and cast your fly fishing rod. Or you can go to the bank and make a deposit. Those are two different meanings of the word bank. And I could use priming to make it more likely that you would think of one meaning or the other. Okay. I don't think I'll step through this again because I know you have a whole chunk on it already. But again, I hope you go back over this. Maybe I'll just highlight a few things. Think about recency effects. Think about expectancy effects. Think about this. Let me go back. Think about the fact that some letter combinations go together more likely than others. So we have some sort of learning based on probability. The human brain is fantastic at probabilistic learning, probabilistic inferences. So things that are more likely. CL go together pretty well. CR, fine. CP, not so much. And of course, you know that if you've gone through the other lecture, that you already know that this is that this one you're looking at here does not show the bigram. But if we go to This one we see a bigram level, which is taking advantage of the fact that based on experience, we have some letter combination knowledge. Let's go back. Where are we? Receptive fields. I'm not sure if I've used this word with you or not. A receptive field, it's not a clear word based on how it's what you'd guess. The receptive field of a neuron is the thing out in the environment that makes the neuron fire. So if you're a neuron in the visual cortex that fires to horizontal lines out in the world are part of your receptive field. Neurons have thresholds, and this is, of course, what we're looking at now is not a neuron at all. It's a neural network. But we like our neural network more if it sort of works like a real brain. Repetition and frequency, again, real important. This first model, fails to explain errors, like like the book has the CQ example. I think it was CQ. This does not have a bigram level. Add the bigram level and it works a lot better. And then, yeah, again, you can step through this again on your own if you'd like. But I know you've been through this, so this is just to make your head spin. A much more complicated model. Not really important for our purposes. Just more important is to understand that really basically the lessons that we gleaned from the model: repetition, frequency, bigrams, regularization. That's a really important concept in this whole top-down processing of words. Now, let's get back to view dependent and view independent. This is a graph from the book, and this shows that faces, when we present them upside down or right side up, we have a higher cost of inversion for faces as compared to houses. So in other words, if we see a house upside down, it slows us down a little bit, but not so much. If we see a face upside down, it slows us down a lot relative to look how fast we are at faces. A couple interesting things in this graph. First of all, you can identify faces faster than houses. Faces are probably the most important stimulus for social cognition. Humans are social animals. Our survival depends on our ability to understand and interact with others in our species, other people. We're incredibly good at it. And to understand other people, you have to understand faces. So you're a face expert in the way that you're probably not expert in any other single visual stimulus. So that's one point. Face is better than houses. But look over here, the cost of inversion is higher for a face as opposed to another object. So faces are very viewpoint dependent. This, I think, is really clear in the book. Margaret Thatcher, upside down. The picture on the left looks a little odd, but not super odd. Yeah, it's like, yeah, it's not quite right, but you look over here and it becomes gruesome. We don't like distortion of faces. Again, faces are very special objects. Just seeing them distorted can be kind of grotesque. I think this is somewhat clear in the text. Objects that we have a lot of expertise on, we tend to see more viewpoint dependence. In other words, well, if you are a bird expert, you'd have more difficulty identifying one bird from another if they were inverted, as compared to if you were not a bird expert. It doesn't mean that the bird expert would be slower than the non-experts, certainly not. It just means that they would get a relatively bigger cost for inversion for birds as compared to something that they're not expert in. I think this is pretty clear. Yeah, this is a nice exam. So this is a nice time to review what we know about the fusiform face area. We know the fusiform face area codes very specially for faces. However, pay attention to the little section in chapter 4 in which they consider the fact that maybe the fusiform face area, maybe that tissue is really designed to code for things for which we have expertise. This is a raging debate in neuroscience. It's a little bit tricky, and here's why. Probably you don't have expertise in identifying any kind of object except for faces. Unless you happen to be a collector of stamps or a bird watcher or some other person who has special expertise in objects. Some evidence shows that as you develop expertise in objects, the fusiform face area gets activated so let's say we recruit a sample of bird watchers. We show the bird watchers pictures of birds and have them identify them, and those individuals would get activation in the fusiform gyrus, fusiform face area, I should say. I am not a bird expert. One bird looks pretty much like another to me. So if I was asked to identify, a crow from an owl, from a cardinal or whatever, I could certainly do it as long as you didn't get to any hard birds. But for me, you wouldn't see the fusiform face area participating in that task. So the FFA seems especially important for developing expertise. And indeed, interesting to see that people who have had FFA damage can lose their ability to identify other things that are not faces. And don't confuse, when I say identify, I mean one versus another. I don't mean recognize a car as a car, as opposed to a big thing I don't know what it is. I mean an Oldsmobile Cutlass from a Volkswagen Beetle. I think this is clear enough. This is the Greeley experiment. I'm sorry, not Greeley, the Greebull experiment. In this experiment, scientists gave people experience with these Greebles. They're these little kind of sort of like Yoda-looking little animals that they played with. They have these pictures are terrible, but the features are slightly different. This guy has kind of curvy ears. This guy has kind of like horn ears. This guy has kind of like downward horn ears. So these Greebles vary on features, and as people developed expertise with them, they showed fusiform face area activation. So what's the take-home message? Well, one interesting take-home message is that the FFA is very plastic. What that means is it changes with experience. And the other interesting take-home message is that as we get expertise in identifying a specific set of objects, the FFA participates in that identification. So again, it's kind of a raging debate in neuroscience as to whether the fusiform face area evolved as a face-specific object and then was co-opted by this expertise issue, developing expertise. And co-opted means it just came to do, it was designed for one thing, but it also does other things that that are similar. And the other point of view is that it wasn't designed for faces. It was really originally designed for expertise. Composite face effect. What does this tell us? We really like to perceive faces as a whole. It's hard to individually perceive the features of a face. I bet that you have a hard time calling up clearly in your mind your own nose. Like if I said, what kind of nose if I could show you 20 noses and say, pick out your nose, I'm guessing you could do it, or probably, but not as easily as you might think. On the other hand, if I showed you your whole face, well, that's a ridiculous task. If you couldn't identify your whole face, then we would say you have prosopagnosia. And so in this case, when you look at a sort of a blend of two faces, it's hard to just say, well, what pair of whose eyes are those on the A panel? Whose eyes are those? For me, I get the Tom Cruise mouth very clearly. I definitely have a familiarity for the eyes. Offset the picture over here as in B, and it's Harrison Ford. That's of course Tom Cruise. This is just a picture for fun. What's wrong with this picture? Well, you probably think nothing. This is a fine picture of George Bush and Dick Cheney. However, look at both of their mouths. Look at both of their noses. What it is a picture of George Bush and then Dick Cheney with George Bush's face kind of overlaid. They put Dick Cheney's glasses back on, but otherwise it's George Bush's face. I bet you didn't even notice that. And I think that's kind of an interesting way. That's another sort of interesting way to think about this holistic perception of faces. You see the whole, you get to identification, and you're not worried about the details. You don't spend a lot of time individually perceiving features. Like, hey, wait a minute, this mouth and this mouth are the same. And we're going to stop there, and I'm going to load this for you right now. Before I load this, I'm just going to, I'll load this now, and then I will load the couple things that go with it.